thing we're going to talk about is dynamic CMOS logic. So we've learned about NMOS, resistor transistor logic, or NMOS logic. We learned about CMOS logic. We learned about transmission gate logic last day, and we're going to do one more here, which is dynamic logic. And so I'm going to draw a picture. Pictures are better. Okay, let's say I wanted to make a CMOS gate. Let's do it simple. Let's make an 8-input CMOS NAND gate. 1, 2, 3, 4, 5, 6, 7, 8. And we know we would do that. We'd have 1, 2, ... All the 8 P's in parallel, right? And I'd have 8 ends in series like that. And we'd have 8 P, 8 ends, we'd have 16 transistors. That's our 8-input CMOS NAND gate. That we call that a static CMOS because this, once you apply some inputs and you have some capacitance here, you either have the P channels driving the capacitance or the N channel. So the output is 0 or 1, and it's held there. And as long as you have power applied to this gate, it could hold that signal on the output forever, right? Basically, as long as there's power. Now I'm going to make a dynamic version of this. So the dynamic version of this looks like this. It has 1 P. It has our 8 ends, 1, 2, ... And then it has one extra end down here. Okay. So these are our 8 inputs, right? Same here, we had 8 here. And we drive these signals with, just to make sure I use this, you can do it both ways. We're going to use phi. Yeah. I'm just going to use phi here. We're going to call this clock phi. Not omega, phi. Or not omicron. The good Greek letter. So the way this circuit works is, let's say phi, I'm going to draw a waveform. When phi goes low, and then phi goes high, and it keeps repeating. Let's just draw 2 clock waveforms here. So when phi is low, logic 0, what happens is this NMOS, and we'll call this output Z, I don't know. This Z node, there's no path to ground, right? When phi is low, the PMOS turns on, so it just pulls the up output high. So the output goes high. And we actually call that the pre-charge. Doesn't matter what the logic is of these 8 inputs, the output is high. We pre-charge it high. And then phi goes high. So now, and by the way, I forgot to mention, there's some capacitance. So phi goes high. So this PMOS turns off. It opens up. We're still got a logic 1 here because we pre-charged it high. Now the NMOS turns on. So we've got that switch closed. And the output here on this node Z will depend on these 8 inputs. If all 8 inputs were 1, the output would discharge to 0. If any one of them is a 0, the path is open, and the 1 will still remain there. It'll be dynamically held on this capacitor. I mean, there's some leakage current that'll slowly drain it, but to a first order, it stays high. So we call this part this is the pre-charge, and this is the evaluate. Pre-charge, this is the evaluate. So in this phase, when the phi is high, we're evaluating this logic function of these inputs. And it could just stay high, or it could go low, depending on the value of the 8 inputs. And then we go to the pre-charge again, and then it goes up, stays high again. And then the next clock phase, it could go high or it could go low, depending on the 8 inputs. And so this is how dynamic CMOS works. During the pre-charge, we don't have a valid output, but during the evaluate, given a little bit of delay, we'll get a valid output. So this is when we want to look at the signal. You might ask yourself, well, why would I want to do this? Well, the obvious thing, or hopefully the obvious thing, is that we have a lot less transistors. Here we had 16, here we have 8, 9, we only have 10 transistors. And in fact, we can write an equation here. If we have some number down here of n channels, we'll have 2 times n transistors here, right? Because we always, in standard CMOS or static CMOS, for every n channel, there's an equivalent p channel that's connected in the opposite parallel versus serial connection. Down here, we only have for n channels, and then we have 2 extra clock-driven transistors. So we only have n plus 2. So particularly when n gets large, this is much more efficient. It's basically for a large n, it's half as many transistors. And we know half as many transistors means half the area, it means lower power consumption, it means lower cost, and usually higher speed. So this is dynamic. So this is static, CMOS here. And this is dynamic. And why is it called dynamic? It's called dynamic because when this stays high here, we're relying on the dynamic capabilities of storing this value on this capacitor. If I were to make this clock really slow, like say the pre-charge was like this, and then, I don't know, maybe I leave the evaluate for a really long time, like here it was, picosecond generation, 100 picoseconds. But let's say I make this like 10 seconds. Well, I've got a problem here because if I did that, if this was phi and I made this 10 seconds, guess what would happen? If Z was high here, and say I wanted to keep it high, well, what would happen is over time, because right on here, there's these reverse bias diodes, right? Connected to ground, and they will leak. They'll cause a little bit of leakage. It's only like picoamps, but eventually this decays. And as it decays, instead of staying high, our noise margins goes down. If it goes low enough, it doesn't even look like a 1 anymore. So there's a minimum clock frequency. You can't go, you can't leave it for 10 seconds. This usually longest delay is in sort of milliseconds, grandma time or something. But you can't go seconds because it's just the leakage. Just even these capacitors are small, even though leakage is small, after milliseconds it'll usually decay. So this is, and we'll talk about this later again in dynamic RAMs if we get that far. But anyway, this is called dynamic because there's a minimum frequency. This thing you can run at 0. F can be equal to 0. Here, F has to be greater than some F min, right? There's a minimum frequency you can run the circuit at. Hence, it has to be dynamic. It needs to have a clock that runs at some minimum frequency. So that's dynamic CMOS circuits.
Professor.
Yep.
In the last picture you had over there, could you go back for one moment?
Yep.
I'm still having trouble understanding the theory of what pre-charge does. If you could just clarify that.
So when phi is 0 in this mode here, right? That's a 0 here, and that's a 0 here. So the NMOS is open, so this switch is kind of open, right? And this switch up here, this PMOS switch is closed, right? Because a 0 on a PMOS closes it. So there's no path to ground, but there is a path to VDD. So the output just goes to 1. This is logic 1, right?
Okay.
That's what pre-charge means. We pre-charge the value to a value of 1.
Oh, okay. I understand.
Is that okay?
Yeah.
Yeah.
I have another question.
Sure.
And yeah, what you just said is, so you put a output capacitance, right? That is the actually the value of this capacitance.
By the way, this I don't really physically put a capacitance. That's just whatever it's driving. Like, say that's driving an inverter. That inverter has that's a parasitic capacitance. We always have capacitances on the nodes.
So will it be just determined by the NMOS, but not the PMOS?
The capacitance?
Yes.
No, the capacitance is determined by the drain to body and source to body capacitance on here, and the gate capacitance of whatever it's driving.
And here in this case, so the 8 NMOS will change this capacitance too, right?
Effectively, they they won't. We're just, this capacitance on this node, we're going to approximate it by just the output capacitance, which is, you know, there's a drain, the ground connect capacitance here, there's a drain to ground capacitance here, and then there's the gate at capacitance. So there's 3 capacitances that group together. They're all to ground, so we just call it one capacitance.
Thank you.
I also have a question. So if we make a bigger dynamic CMOS logic gate, does it mean that we will have a bigger overall capacitor that will hold the value for longer?
Well, if you make this gate bigger and a bigger capacitance, it will usually take longer to leak. That's true, but then it takes more area and so on. So we don't usually play around with that too much. Normally we would run these at a pretty high speed. Like normally you don't have to run them at milliseconds. We would run these at megahertz or, you know, microseconds or picoseconds. I'm just saying there is a minimum. You can't just put them on hold. We'll see later on. We want to stop a circuit and leave it in some mode. You can't do that with these. You got to keep clocking them.
Okay.
I see on the chat. So dynamic CMOS has a smaller leakage current than static. No, the leakage current is the same for, you know, this one has a leakage current too, right? There's little diodes here, reverse bias diodes that will leak. But the thing is, either the P or N is on, so it can provide lots of current. So it provides the current for this leakage and keeps this charged up or discharged. So it's got enough current going all the time to overcome this leakage, whereas this one doesn't. When I turn them both off during this evaluation, if they're both off, there's nothing to overcome the leakage to keep it at 1. Other question, can you explain what happens in the evaluate phase? I did that. And a smaller parasitic capacitance, I don't know. Is this a difference between it? Yeah, SRAMs use kind of like a static CMOS structure where DRAMs use this dynamic structure with a capacitor. Yep. Any other questions?
Well, wouldn't the leakage current depend on how many transistors you have? Like if you're comparing 8 to 16, I would think that the leakage current in the static would technically be larger, but just being refreshed more. So it wouldn't really matter.
Oh, I'm confused now. So let's take this node with this capacitance is. Now there's only one leakage current from this P channel. You right with that? Okay with that?
Yeah.
And this N channel's got one diode connected there. Now, technically, if depending on how many of these gates you turn on, there could be leaky. There could be more leakage from internal nodes in here as well, depending on the logic value of these 8 inputs. That's
Right.
true. Yeah. But generally, whatever this worst case leakage is, we have to run it fast enough so it doesn't leak that we lose the signal.
Right.
Okay. Let's go back here. So that was the explanation of this slide. Last slide